that we also show the enzymes that are responsible for that metabolism. Now I want us to, any questions so far? Might be going very fast. Do you have any questions so far? Are we okay? Class? Are we okay? I can see we are 39. Jacinta, I think you had given me for this unit, I think you had given me 37. Check again. Check the class. Yes, Jacinta, not Jacinta, sorry. Frida, you had given me that 7. I can see I have 39 logged in. So we need to find out the extra. Let's get a comprehensive list, please. So any questions? Are we okay? Can I get response? Public chat, any issues, any questions, any problems? Public chat, please. Chat me up. Chat me up. Let me know we are together. Yeah, okay, thank you. Though you should say I'm okay, because you don't know about the other person. Might say we are okay, and there's another one who is not okay. So let me get a few of your comments. Are you okay? Because we're just laying the foundation of I'm okay, thank you, I'm good, very good. At least that way, let's keep chatting each other so that we move together without anybody indeed being left behind. We are all important. All of us are very important. And therefore, each and every student, each and every one of you means a lot to me. And I do not want to leave anybody. Like now you're in second semester or 5th year. What? I don't want anybody to be left behind. And yet, you know the experience of farm care. Cheza kidogo, utaachwa nyuma, utasema mwalimu ni mbaya, lakini mimi najua, I've assessed myself now, and I know I'm not bad. I know I am a bit sick, but if you give me what I need, you will pass. So just be attentive, be there, learn to ask questions, and we'll be good to go. Then we're now looking at the types of opioid receptors. And we have, as I had said earlier, we have mainly 3 types of receptors. We have the mu receptor, we have the kappa receptors, and we have the delta receptor. A bit, sometime back, they also used to think of the sigma receptor, but those receptors were dropped. So we have the mu receptors, and the mu receptors are responsible for supraspinal analgesia mediated by the mu1, and also spinal mediated by mu2. So we are only saying the mu receptor are responsible for analgesic effects. They are also responsible for respiratory depression and gastric motility reduction, which is mediated by mu2. So most of these people who are using these drugs also have a lot of constipation. They have a lot, and actually constipation is quite a major side effect. Respiratory depression is usually the killer. The spiritual depression is usually the killer of these people, especially as you get tolerance, addiction, you continue. Remember, tolerance is where you have to increase the dosage so that you get the same effect that you were getting initially with smaller doses. So what happens is every time, today, this week, perhaps you're using, let's say 10 milligrams, and you are good to go. Then you develop tolerance, and you find that, now when I inject 10 milligrams, I cannot get that effect that I was getting and that my body is used to. So instead of 10, you go to 15. Ignoring that also there are also some side effects. So you continue increasing until, because these drugs are also causing respiratory depression, until now you give a dose that completely, that gives you total, gives you a lot of respiratory depression and therefore death. So that is how it happens, because you have tolerance, there is addiction, you can't stay without it, and the tolerance means you continuously increase the doses. So you increase the doses until you get the lethal dose or the fatal dose that will definitely kill. So those are the mu receptors, which are responsible. So the depression and gastric motility reduction is mediated by mu2 subtypes. Also, the mu receptors produce euphoria. These are now the things these people want. They are euphoric. You are higher than everybody else. Some of them could tell you they can fly, and so on. And there is also physical dependence and meiosis. Then, therefore, those are the mu receptors. Then you have the other receptor, is the kappa receptors. Again, I will not go into details to this because I know pharmacologists are better than me in this. So I definitely know you will mention, if you haven't, you will look at these receptors in pharmacology. So we have also the kappa receptors. They appear to mediate against spinal analgesia at kappa 1 subtypes and supraspinal analgesia at kappa 3 subtypes. Remember, we did mention for the mixed agonist antagonist, it can be an agonist at mu receptor and an antagonist at kappa receptor. And you can see also, even the kappa receptor, when you talk about analgesia, it's also causing spinal analgesia. So if it's an agonist at the mu receptor and it is blocking the kappa receptor, that is why we call it a mixed agonist antagonist. It produces respiratory, again, depression, dysphoria, hallucinations, meiosis, sedation, and nicotinic effect. So you can see again that is the respiratory depression major in causing the deaths of many of the abusers of these drugs. Of course, the dysphoria, the hallucinations are some of the things that these people want. One can understand why, but those are the effects of the kappa receptor. Then you have the gamma receptors. And activation of the gamma receptors produces, again, spinal analgesia, respiratory depression, affective behavior. Affective behavior is when you improve in whatever you are doing. When you talk about the affective behavior, is that when whatever you are doing, you do it better. Affective behavior, reinforcing actions like when you talk about an animal and you are giving it, let's say you are training it, you train it, you keep some food away and you are training it to go for the food. And then you withdraw the food. So you train it to go for the food, And what happens is that now if you give those animals the morphine, you find like the speed. When you are training them initially to go the food, they were going at 10, let's say that's 10, can we say 10 kilometers per hour, let's say 10 kilometers per hour. Now, when you give the morphine, you might find they're even going at 200 150 kilometers per hour. That is what we are calling the reinforcing actions. That these drugs, when you give these drugs, they increase the behavior, they reinforce the actions they reinforce the actions of whether it is the animal, of course, even the human being. So the person who is taking these drugs, some of the actions will be reinforced because of these drugs. They also reduce the GIT motility. Again, a big issue in causing constipation, and as we have said, that is a major side effect of these drugs. So we are saying the reinforcing action is anything that strengthens or increases behavior. So that these are drugs that will strengthen or increase behavior. And also when we talk about affective behavior, is any behavior that reflects an individual's level of professionalism, any behavior that reflects an individual's level of professionalism, be it punctuality, initiative, respect for peers, judgments, the judgments a person makes, response to direction, attention, in doing whatever they are doing. So that's what we're calling the affective behavior. It is where it is that which any behavior that reflects an individual's level of professionalism. That is what we're calling the affective behavior. And as I have said, the reinforcement, mainly seen, especially the reinforcement can be, as I've said, can be seen in animals when you are training them. And when you train them to go for something, or you're giving them some, what is it called, like a bait, then you find that they You're giving them some reward. You see, when they do a certain action, you train them. And when they do a certain action, you reward them. So all we are saying is that it was found when you did that. And first of all, you test them without giving them drugs, the narcotic analgesics. When they were given the narcotic analgesics, then it was found that when they were going for the reward, the speed of going for the reward is really high. In other words, the morphine has reinforced those particular actions. So those are the three receptors, the mu, the kappa, and the delta, and they are the ones that are responsible for, those are the receptors that are bound by morphine and are responsible for the activities of the morphine and analogs. Mechanism of action: the opioid analgesics agonize, or they bind the opioid receptors, mu, K, and delta, which are G protein coupled receptors. I believe you've done that a lot in pharmacology. So you have these three receptors, mu, K, and delta. We just discussed what they're responsible for, and the G protein coupled receptors. And once these drugs bind these receptors, we are saying it leads to a series of events which ultimately block neuronal pain transmission. So ultimately, the work, or what the morphine and analogs do is to block neuronal pain transmission. Once the pain is not transmitted through the neurons, then definitely you don't have any pain at all. How do they do it? One, they do inhibition of activation of voltage-gated calcium channels and depress neurotransmitter release. So they will depress the neurotransmitter release. Remember, the neurotransmitter is the one which crosses the synapse where there is a gap. It helps to transmit the information between I think it was a cell body and the beginning of another neuron. So it helps that gap. It helps to transmit the information in that gap. And therefore, once you block the neurotransmitter release, you will block chemical transmission. You will block chemical transmission, and therefore the message will not be relayed. The pain message will not be relayed, and therefore there will be no pain. It will increase potassium conductance outside the cell to cause hyperpolarization of the cell, thus reducing its excitability. Once you have hyperpolarization, the cell cannot be excited. They also, adenyl cyclase, the inhibition of adenyl cyclase. Adenyl cyclase is very, very important. It's an enzyme that brings about the formation of cyclic AMP, adenosine monophosphate, and the cyclic adenosine monophosphate is important in phosphorylation of the ion channels. And once the ion channels are phosphorylated, there's increased chances of channel opening. There's increased chances of channel opening. So once you inhibit adenyl cyclase, you will have decreased chance of channel opening. And these are the channel openings, the calcium-gated channel opening, and therefore, once the calcium channel opening does not happen, then you will have blocked neurotransmitter release. So those are the three main ways in which these drugs bring about their activity. And it's also here, opioid receptors act on G protein coupled receptors, inhibits adenyl cyclase, promotes opening of potassium channels and inhibits openings of calcium channels, reduces neuroexcitability and increases potassium conductance, and ultimately it causes hyperpolarization and slows. And I think this brings about inhibitory slows inhibitory pathway and release pain. I think I would say causes hyperpolarization, shows inhibitory pathways. Cannot show, so it activates, I think it's like activates inhibitory pathways and relieves pain, because shows it does not make sense. So I would say causes hyperpolarization and activates inhibitory pathways and relieves pain. So we have opioid receptor, acts on G protein coupled receptors, inhibits adenyl cyclase, promotes potassium channels, and so on, reduces neuroexcitability. So ultimately causes hyperpolarization and either slows, you can even, not slows, activate inhibitory, because if it slows inhibitory pathways, then you will not have any activity. So activate inhibitory pathways and relieves pain. So that is our mechanism of action. So through cyclic, So through adenyl cyclase, through the potassium channels, and also the calcium channels. SAR, structure activity relationship. For us to understand the structure activity relationship of morphine, the first thing we must understand is the structure. We have already looked at, we have said we have the pentacyclic ring structure, which is rigid, consisting of an aromatic ring and two cyclohexene rings and a dihydrofuran ring. And of course, in the periphery, we have a phenolic hydroxyl group at position 3. We have an alcoholic hydroxyl group at position 6. We do have a tertiary amine at position 17 and a double bond at position 78. Those are the main features of morphine. And perhaps those are some of the features that, or some of the structural features, or some of the structural functions that we want to interfere with, we want to change, so that we can change the activity, we can change the binding ability of this molecule so that it binds better. And of course, also it's more selective, it binds better, it's more selective. And indeed, if it is more selective, then perhaps it will be able to lessen the toxicity. So we'll start with stereochemistry. We have already mentioned it has 5 chiral centers, and only the laboratory isomer is active. That is, we have mentioned, and we have said carbon 5, carbon 6, carbon 9, 13, and 14 are the ones that display or exhibit chirality. 5, 6, 9, 13, 14 are the carbon centers that exhibit chirality. And once, of course, they exhibit chirality, we expect that, of course, as we have said, that they will have optical activity. They will have a specific configuration. Once we say they are chiral centers, we expect them to have a specific configuration whereby we have discussed earlier. You can have the S or R configurations. We go to the next point. It exists as a single naturally exists as a single naturally occurring laboratory yes, correct. Laboratory isomer with 5R, that is now the specific stereochemistry, 6S, 9R, 13S, and 14R configuration. So not only are we having that these 5 carbon centers, or these 5 centers are chiral, they also do have specific configuration at their particular point, so that the ultimate is a laboratory molecule. So 5R, 6S, 9R, 13S, and 14R configuration. It can undergo epimerization with carbon 14, but that has no the effect or benefit on analgesic activity. You remember epimerization, we said, is when you have a change of the configuration at a particular carbon atom. So like if you have that particular position, some of the important group change their orientation. If a group was carrying the alpha orientation, it acquires a beta orientation, and therefore, of course, the stereochemistry of that point changes. So we are saying position 14 can undergo epimerization, but it has been found to be of no relevance or no significant benefit in analgesic activity. So therefore, again, when we look at this molecule, here we are saying that it is 5, 9, 13, 6, 5, 6, 13, 14, 5, 6, 9, 13, 14. And those, of course, as we have just said, those particular positions, you can be able to see, indeed, the 5, the first is 5, it's R, the second one is S, the next one is R, the next one is S, and the next one is R. So it's easy to know. As long as you remember that the first one is R, and then you remember the carbons are 5, 6, 9, As long as you remember, of course, these ones, even if you don't remember, you look at your molecule and you can identify the chiral centers. But what I've seen, it's like there's a pattern. The 5 is R, the next one is S, the next one is R, the next one is S, the next one is R. You have always to look for a method of remembering, so that makes us remember easily. So we are looking at position 5, R, position 6, S, and then position 9, R, then from 9, 13, S, and 14, R. So that is a specific configuration or configuration of the morphine molecule, and you require it to remain like that for optimal analgesic activity. Remember, somewhere we did mention that the analgesic activity correlates with also the addiction and dependence. So when the molecule has very high analgesic activity, it also has a very high degree of addiction, high degree of dependence, and so on. So they go hand in hand. The higher the analgesic activity, also the higher the toxicity. Then the hydroxyl, these are some of the things that we've mentioned. I hope you still have some time. It's always good to be careful about time. Oh, I've only 1 minute. I think I can just finish that slide. Oops, I missed. So we can, because again, this is repetition, we've done this, but it's now trying to arrange the points in our minds. So we're looking at morphine as here, the hydroxyl group in the phenolic ring, and the basic nitrogen is needed for activity and seen in all potent mu agonists. Hydroxyl group in the phenolic. So this is a 3-hydroxyl group. We are saying the 3-hydroxyl group and the basic nitrogen are needed for activity and are present in all potent mu agonists. And we will see, actually, we do require not only usually just a hydroxyl group, we require actually a free hydroxyl group for maximum analgesic activity. Activity can be preserved or enhanced by removing other rings. And as I have said, when we look at as we continue developing our narcotic analgesics or morphine analogs, you see you can remove. At one point you say, you remove the ether linkage. And then at a particular point, we will say, remove the C ring, the whole of this C ring, remove it. So we are saying, that's why we are saying, this is general, but we are going to see it as we move along. And as you remove the rings, of course, you get a different class of drugs. And that different class of drugs is still good in its activity. So we can't say activity can be preserved or enhanced by removing other rings. So that I have said, like when we talk about the morphinans, you say they do not have this ring. Like you remove the epoxide ring, so they will have 1, 2, 3, 4 without this either bridge. And those drugs are still active. Then you get to a point, as I say, you remove the whole of the C rings. And now, therefore, so you have removed the epoxide linkage, you have removed the C ring. That means you are left with A, B, and C. You have been removed, left with A, B, and E. Was E. But therefore, those drugs will have only 3 rings, unlike, of course, our fast drugs that have 5 rings. So that's what you're saying. We can really remove the rings, and the molecule will still have activity. Changing the hydroxyl group to just hydrogen, or a methoxy group lowers activity, as seen with codeine. We are only saying, you see, this is our 3-hydroxyl group. We are saying this 3-hydroxyl group requires to be free for maximum activity. If you change it to a hydrogen, you reduce activity. If you esterify it to a methoxy group, you get codeine. The difference between codeine and morphine is very simple. Codeine has a methoxy group here. Morphine has a hydroxyl group here. So in other words, we did mention morphine can be metabolized into codeine. We said it's a minor route of metabolism, whereby there is oxidative methylation. There is a methylation here, not oxidative methylation. There is methylation to give us codeine. And codeine, incidentally, is a different molecule. Of course, it has very low addictive properties, very, very low, but it acquires a new characteristic. Codeine is an antitussive. In being an antitussive, it means it can be used in cough syrups to stop cough. It is an antitussive used in cough syrups to stop cough, just by the virtue of changing this group from a hydroxy group to a methoxy group. You decrease the analgesic activity, you bring in a new activity, and the drug, of course, it still has some addictive power, but it is a safer drug anytime than morphine. But there are also people who do abuse codeine. So the nitrogen, so that, please do understand, so changing the hydroxyl group to hydrogen or a methoxy group lowers activity as seen with codeine. We will also see you can change this into an acetyl group and also this into an acetyl group. When you change this into an acetyl group, change activity slightly. When you change this into an acetyl group and that into an acetyl group, you get the drug we call heroin. So heroin is this being OC double bond, OCH3, OC double bond, CH3, acetyl group, you get heroin. It's still a derivative of morphine, but very powerful compared to morphine. So we are saying the nitrogen is most, so we have finished with that, but we're going to see very many examples. We're just looking at the general SAR as, of course, we zero in to the very, very specific SARs. The nitrogen is mostly tertiary with a methyl substitution in morphine, but in other drugs, we have other substituents. We have the antagonists. I believe when we are looking at the classification, I mentioned naloxone, naltrexone. They have earlier substituents here. They have different substituents here, and they become antagonists. The size of the substituent or nitrogen dictates potency and agonist or antagonist activity. So when you change this group into an allyl group and to other group, then you change the activity of the morphine. And again, we'll see quite a number of examples. As I've said, these are very general as we go back to do the very specific. Reduction of the 7-8 double bond increases activity. So this is a 7-8 bond, and therefore we will see hydromorphine, hydrocodeine. So if you remove that double bond, normally this double bond is not removed on its own. Normally you remove that double bond and this group here, you oxidize it to a ketone. So you remove that double bond, oxidize this, and you get the morphones, the codones, and so on, and they are very active. So what we are saying is that you do not require that double bond. Indeed, even as we move on, we see you do not, I don't know whether that is what, as I'm finishing, inclusion of a hydroxyl group at position 14 increases activity. So at this position here, you can have a hydroxyl group included there. When you put a hydroxyl group there, the resultant drugs, you call them oxycodone, oxymorphone, once you introduce a hydroxyl group there. I will still repeat this next time as we start. Removal of a hydroxyl group at position 6 increases activity. You cannot interfere with this group. You cannot remove it, but you can remove this group with increase in activity. So we are looking at just the general ones. Oxidation of the hydroxyl group to ketone. The 6 hydroxyl group to ketone group at 6 increases activity. If there is also reduction of 7-8 double bond, e.g. hydrocodone, as I've just said. So normally, oxidation of this hydroxyl group goes hand in hand with saturation. This is an unsaturation. Saturation of this or reduction. You know, reduction is also addition of a hydrogen. So reduction of this 7-8 double bond goes hand in hand with oxidation of the hydroxyl group at position number 6 to get either the morphone, the codon, and so on, and then you remove that double bond. That further increases activity. Acetylation of the hydroxyl group at 6 increases activity. If you acetylate that hydroxyl group, as I said earlier, and acetylate this hydroxyl group at position 3, and you get 3,6-diacetyl morphine. That is what we call heroin. That is what we call heroin. And heroin is one of the very dangerous drugs, one of the very highly active drug in terms of analgesic activity. And we have already said the higher the analgesic activity, the higher the toxicity. Removal of the ether linkage produces compounds we call the morphinans that have increased activity. So that you can remove this safely and you will not have a problem. I think because of time, although we started a little bit late, as I have said, we will start again here. And now we will look at the different categories. We will now start looking at each of the different groups, whereby we will go individually. We will look at each substituent and see what derivatives or which drugs can we derive from changing that hydroxyl group, from changing that other hydroxyl group at position 6, from bringing about saturation at that position, adding a hydroxyl group there, changing this group here. There is even also another linkage that you can do here in between here. So we will now look at this drug we are calling morphine and change it, break it down so that we get the different classes of the morphine and morphine analogs that indeed are there out in the market, and they are being used clinically for both, for either as an antitussives, as I've said. Some are being used as antidiarrheals like loperamide, dextromethorphan, loperamide being used as antidiarrheals, and others like pethidine, which is meperidine, being used even in labor ward for analgesic pain. So I think with that, I hope you have learned something today, and we can call it a day. I have how many? 39. I hope all of you. I cannot see anybody who is offline. Wow. Do I read these names quickly so that you tell me who is the extra person? Can I read your name quickly? Please allow me to read it very quickly so that I know who is extra, not Mark. Let me read them very quickly. There is Chemtai Ruto, Dorothy, Otieno, Anyango,